In today's video, what we're going to do is take a look at the size of an atom. Just to review where we are at this point, we've uncovered reasons to believe that everything is made of atoms, that atoms are the basic unit of all matter, and that chemical change is just a rearrangement of atoms. It's never atoms being created or destroyed or altered. And then we also came to realize that the atoms aren't indivisible, as John Dalton originally thought, but in fact that atoms are made of smaller particles, protons, neutrons, and electrons. Here's an example of our kind of modern view of the atom. This is a carbon atom, and it's got 6 protons, 2, 3, 4, 5, 6 protons, and that's what makes this a carbon atom, the fact that it has 6 protons. That's called carbon's atomic number, and it's a characteristic of any atom that's carbon. It's got a number of neutrons. That number of neutrons can vary, and it's got electrons, and in a neutral atom the number of electrons and the number of protons is the same, and that's what we've got here, 6 electrons. Now we turn ourselves to the question of how big is an atom. And if you're asking how big is an atom, there are really 2 questions that you can ask about how big something is. Like, how big is an elephant? You could ask how tall it is, how wide it is, how much space it takes up. That's one question about the size of an elephant. But the other question that you could ask is, how much does it weigh? So we're first going to take a look at its volume, and then we're going to look at mass. So what's the volume of an atom? Well, atoms vary in size. They're not all the same size. But the radius of a typical atom is about 10 to the minus 10th meters. So that's the distance from the center of the nucleus out to the farthest out electron, roughly 10 to the minus 10th meters. Now, people who measure atoms all day long get tired of writing 10 to the minus 10th, and so there's a new unit that they've developed that's called the Eckstrom. It's named after a guy, and the symbol is a capital A with a little halo above it. That's an angstrom, and that's 10 to the minus 10th meters. So an atom is about an angstrom across. So what's the volume of an atom? Well, assuming that an atom is a sphere, which is roughly true, 4/3 times pi times the radius cubed is the volume of a sphere. So the volume of an atom would be about 4/3 times pi times 10 to the minus 10th meters cubed. Or if we put this in a unit that's what we usually use for measuring volume, it would be 4/3 times pi times 10 to the minus 8th centimeters, quantity cubed. And pi and 3 roughly cancel out, so we're going to have a mantissa that's about 4, but the mantissa isn't really important when the numbers are this size. This comes out to 10 to the negative 24th cubic centimeters, or 10 to the negative 24th milliliters. Now, it's hard to even comprehend how small that is. That's decimal point, 23 zeros, and then a 4. That's the size of a typical atom. What's a cubic centimeter? Well, if you think about the space of a sugar cube, that's about a cubic centimeter. It's about a centimeter by a centimeter by a centimeter. Inside that space, here's what that means. You could fit 10 to the 24th atoms inside the volume of approximately a sugar cube. How big is that number? Well, 10 to the 6th is a million. 10 to the 9th is a billion. 10 to the 24th is 10 to the 9 times 10 to the 9 times 10 to the 6, because 9 and 9 is 18, 18 and 6 is 24. So that's how many atoms are in there. A billion, billion, million atoms. Maybe this will help illustrate this. This jar here that you can see sitting there has a million of these little tiny beads in it. You can see how big the jar is. There's a candy corn like you see at Halloween time. Here's a can of Mountain Dew. So this is a jar that's about a gallon in size. Inside there, these little teeny tiny beads, a million of them fit in there. So if I had 1,000 of these jars, I would have a billion. If I had a billion of those thousands of those jars, I would have a billion billion. And then if I had a million of those, I would have how many atoms can fit in a sugar cube. Just for comparison, I figured out the math one time, and if I had beads that are like this in this jar, the same size of beads that are like the ones in the jar, and I stacked them over the surface of the earth until I had 10 to the 24th, the stack would be over 1,000 feet high. That includes Alaska and Hawaii. So there are an incredibly large number of atoms in the volume the size of a sugar cube. So that means they have to be incredibly small. What's remarkable about atoms is that they're made of particles that are even smaller yet. The nucleus, for example, has a radius of about 10 to the minus 15th meters, which would be roughly 10 to the negative 5th in angstroms. Well, 10 to the minus 5th is 1/100,000th. So that means this is 100,000 times smaller than the entire atom. So that nucleus that's in the middle there doesn't take up very much space at all, and the atom is 100,000 times bigger, and that means in between the atom is mostly empty space. Here are a few analogies for comparison. Imagine the nucleus was the size of 1 grain of sand. The distance from the nucleus to the farthest electron at that scale would be about a football field. So the atom would be 2 football fields across if there was a grain of sand in the middle, and that was the nucleus. Here's another analogy. If the nucleus was the size of the Earth, the nearest electron would be as far away as the Sun is from the Earth, 93 million miles. Here's another one. If the nucleus were the size of a basketball, the atom would be about 2 miles across. So imagine here's the high school, here's Walmart, right in the middle is an atom the size of a basketball. That's how big the atom is. That's the closest electron. All the rest of that's empty space. So that gives you an idea of the volume of an atom, and it's not very big. Now let's turn to the other question, which is, what's the mass of an atom? Well, the mass of an atom is going to be the mass of all of the subatomic particles that are in the atom. So protons, neutrons, and electrons are what we call subatomic particles because they're under the category of an atom, or they're smaller than an atom. So the proton's the first one. We have a symbol for protons, P, and then a little superscripted plus sign to show that it's positive. So P for proton, plus for positive. I'm going to fill in some information about these subatomic particles. One is the charge. The charge on one proton is 1.602 times 10 to the negative 19th coulombs. Coulomb is a standard unit of charge. You don't have to really understand what that means at this point. The mass of a proton is 1.673 times 10 to the minus 24th measured in grams. So that's a millionth of a billionth of a billionth of a gram. So it's very small. Neutron has the symbol N for neutron, superscript 0 for no charge. So, no charge. Its mass is 1.675 times 10 to the negative 24th grams. Almost exactly the same as a proton, but not quite. In the thousandth of a millionth of a billionth of a billionth, they're different. The electron is E for electron, negative sign for negative charge. And its charge is minus 1.602 times 10 to the minus 19th coulombs. You might see a similarity between that and the proton's charge. The mass of an electron is 9.110 times 10 to the negative 28th. So that's 4 orders of magnitude different from a proton or neutron. It's smaller. Now, instead of writing all these big numbers all the time, physicists and chemists that work with this stuff have chosen to look at relative values. So if we look at the proton, neutron, and electron's charge, what's highlighted in pink here, you may have already noticed that the proton and the electron have the exact same charge, except one's positive and one's negative. So how we deal with that is we just call a proton plus 1, and a neutron 0, and an electron minus 1. Rather than writing out in coulombs, we just make a new unit, relative atomic charge. And that's a lot easier to deal with. So you won't see coulombs again in this class, but you will see plus and minus a lot used to describe the charge of protons and electrons. We can make a similar simplification with mass. If you look at the mass of a proton and neutron, as I already have mentioned, they're almost exactly the same. If you look at the mass of an electron, it's 10,000 times smaller. So here's what we do with that. There's a new kind of unit that's called an atomic mass unit. The atomic mass unit is approximately the mass of a proton or a neutron, but it isn't exactly the same. We abbreviate it 2 ways. One way to abbreviate it is AMU for atomic mass unit, or just U for short. Because the atomic mass unit is approximately the mass of a proton or a neutron, we say that a proton's atomic mass is about 1. A neutron's atomic mass then would also be about 1. Well, The electron's atomic mass is 0.0006, which is practically 0 compared with 1. Now, because most of the mass of an atom is the protons and neutrons, and they're in the nucleus, the mass of an atom is mostly the nucleus. So the mass of an atom in use is about the sum of how many protons are there and how many neutrons are there. So we're ignoring the mass of the electron when we consider this in this simplification. And that number is called the mass number. So the mass number is the sum of all the protons plus all the neutrons that are in the nucleus. And it's about what the weight of the atom is in use. So what's the mass number of this atom here? Well, it's an atom of carbon. We can see that because it's got 1, 2, 3, 4, 5, 6 protons. It's also got 1, 2, 3, 4, 5, 6 neutrons. So the mass number of this particular atom is 6 for the protons plus 6 for the neutrons, or 12. Try this one. Well, if you can count fast, you've already realized that you still have 6 protons, so it must be the same element. It's carbon. This time, however, you have 1, 2, 3, 4, 5, 6, 7 neutrons. So our mass number is 6 plus 7, which is 13. Here's another atom. If you count the protons, you still find 6. 1, 2, 3, 4, 5, 6. If you count the neutrons now, you have 1, 2, 3, 4, 5, 6, 7, 8. So this mass number is 14. All of the atoms that we had in these last 3 examples have 6 protons. That means they're all carbon, but they have different numbers of neutrons. Those are examples of what we call isotopes. Isotopes are atoms that have the same number of protons. In other words, they're the same element. But they have a different mass number. In other words, they have different numbers of neutrons. How can we tell all of these were carbon? Because of the fact that they all had 6 protons. How could we tell they're not exactly the same atoms? Because they all have different numbers of neutrons. So isotopes have the same atomic number and different mass number. There are 2 ways that we use to describe isotopes to kind of identify which isotope we have. One is called hyphen notation. In hyphen notation, you write down the name of the element, which in all of these cases would be carbon, and then you put a hyphen, and then after that you put down the mass number. Well, this one had 6 protons and 6 neutrons, and so that adds up to 12, so this is carbon 12. This one has 7 neutrons with 6 protons, so 7 and 6 is 13, so this is carbon 13. And then this last one had 8 neutrons with 6 protons, so that's 14 mass number, so carbon 14. Another way we can do this is with what's called a nuclear symbol. And with the nuclear symbol, we write down the symbol of the element, C here for carbon, and then we subscript the atomic number to the left. That would be 6 for carbon in every case. And then we superscript the mass number, which for this isotope was 12. For the middle isotope, it was 13. For the right-hand isotope, it was 14. Now, if we subscript the atomic number, it's always going to be 6 for carbon, so some scientists just leave off that atomic number. Here's an example, hydrogen 2. What would this be in symbol notation, nuclear symbols? Well, hydrogen is the symbol, atomic number 1, mass number 2. Fluorine 18, F for fluorine, subscript the atomic number, which is 9, and then superscript the 18. Not too hard to do. You try one. U for uranium, 92, because that's uranium's atomic number, and then the mass number is 235. Here's what I'd like you to do. Using what you know about isotopes now, fill in this chart. Stop the video, and on your notes, just fill in all the missing information here. And then I'll come back and do it too, and you can see if you're right. Well, the hyphen after neon is followed by a 20, which means that's the mass number. So I can put a 20 down here for mass number. If it's neon, neon is element number 10, so that's the number of protons, that's the atomic number. The difference between the mass number and the number of protons has to be the number of neutrons, so there must be 10 neutrons in this isotope. Now to do the symbol, we'd have to write neon, and then 10 goes down here, and a 20 would go up here. In the next row, all we have to go off of is the nuclear symbol. But that's enough, because we know that the mass number is 21, so we can put that in this column. We also know that it's neon, so we can do the hyphen notation, neon-21. The number of protons has to be 10 because it's neon, and the difference between the mass number and the number of protons is the number of neutrons, so that must be 11. The next row we have only the protons and neutrons, but if we add them together we get the mass number. So 10 and 12 is 22, that's our mass number. If there are 10 protons, then we know that that's neon. Now that we know that the mass number is 22, we know it's neon 22. And the nuclear symbol, neon for the element symbol, 10 for the atomic number, and then superscript 22 for the mass number. On the periodic table, the mass of an atom is listed for every element. Here's a sample square from a periodic table for hydrogen, the very first element. If you look at the atomic mass, which is circled here in pink, you'll see that it's 1.0079. Let's look at another one. Oxygen is 15.999, atomic number 8. Carbon, atomic number 6, is 12.011. Here's iron, 55.847. You can look those up on the periodic table, and we do it all the time. It's very useful information. But what we find is that none of these numbers comes out to whole numbers. Here's why. There are 3 reasons. First of all, if you're being really precise, the masses of the electrons aren't really equal to 0, and so you have to count for the mass of the electrons. They're very, very small, but they really aren't 0. Second of all, the atomic mass unit isn't really the mass of a proton or a neutron. In fact, it's defined as exactly 1/12 of the mass of an atom of carbon-12. Now that is really close to a proton's mass or a neutron's mass, but it isn't exactly. And so just adding up the mass number doesn't really give us the atomic mass. And then the third reason, and this is the one that accounts the most for the discrepancy, the atomic mass that's given on the periodic table is really an average of the masses of all the isotopes of that element. And this isn't a normal average like add 3 things up and divide by 3. That gives equal weight to all 3 numbers when you do it that way. And that's the typical way we find averages. But this is what's called a weighted average. So a weighted average gives more value in the average to the weights of the isotopes that are more common. Here's how it works. If we wanted to find the average atomic mass of chlorine, there are 2 isotopes, chlorine-35, which has this atomic mass, and chlorine-37, which has this atomic mass. Now, 75.77% of all the chlorine in the universe is a chlorine-35. The rest of it, 24.23%, is chlorine-37. So here's how we do a weighted average. We first of all take chlorine-35's atomic mass, which is 34.9689 U's. And we multiply that by the relative abundance, which is a percent, but we're going to turn it into a decimal, 0.7577. Then we're going to add to that the same product for chlorine-37. So 36.9659 multiplied by 0.2423, which is the relative abundance of chlorine-37. And when you do this, you come up with 35.45. 35.45 is a lot closer to the mass of chlorine-35 than it is chlorine-37. Why? Because there's more chlorine-35. So on average, it's going to be closer to that number. You try one. Find the average atomic mass of nitrogen from the information given in this table. Pause the video, give it a try, and I'll come back and give you an answer. Okay, here's our answer. Nitrogen 14, atomic mass is 14.0031 U's, and I'm going to multiply that by the relative abundance, which is 0.9963. Then I'm going to add to that 15.0001, because that's the atomic mass in U's of nitrogen 15, but its abundance is only 0.37%, so that's 0.0037 in decimals. When I put this all together, I get 14.01. If I compare this to the periodic table tells me 14.007 is the atomic mass. I have pretty good agreement there.